Welcome to this video. Here I describe how I built a do-it-yourself ice chest air conditioner for my airplane. We'll start by describing the problem that we're trying to solve. Then we'll talk about the options that are available to pilots to try to solve that problem. Then I'll summarize and show you the end result of my particular solution. Finally, I'll walk through the key materials used along with the step-by-step instructions followed in order to construct this unit. First, let's describe the problem that I'm trying to solve. As most pilots know of general aviation aircraft, especially older aircraft, most of them don't have built-in air conditioners, so it can get really hot inside the cabin, especially during the summer, during the phases of the flight, such as engine start, taxi, takeoff, and climb to altitude, and then the eventual descent, landing, and taxi to parking or back to the hangar. The usual options of what one can do about it is, first of all, install an FAA-approved integrated liquid refrigerant air conditioner running off a compressor that's connected to the engine. This is much like an automobile system is. Many times, though, especially for older airplanes, these aircraft air conditioners are an aftermarket item or otherwise purchased and installed for a very large expense, on the order of $20,000 or more. The second option is to install via STC, a self-contained liquid refrigerant air conditioner running off electrical power that's supplied from the engine. Arctic Air, for instance, has a line of these air conditioners. But the problem is they're still very expensive, starting at about $5,000 just to purchase the unit. Plus, usually requires the installation of a high amperage alternator, breaker, and wiring to run that significant electrical current to the unit itself. The third option, and what many people default to, is to purchase a commercially available self-contained 12-volt ice chest that cools cabin air by pulling air through a small radiator through which ice-cold water is circulating. The issue, however, is the unit is still a little bit pricey, on the order of $500 to $800, comes in a limited set of sizes and capacities. I believe the largest size available from Arctic Air is 52 quarts, and can, depending on the unit, draw an electrical current that exceeds most capabilities of cigarette lighter adapters in aircraft. The solution I chose was to build a custom do-it-yourself ice chest air conditioning system. To fill my particular baggage compartment, I was able to construct a unit that was bigger than the largest commercially available units made specifically for airplanes, namely the 52-quart Arctic Air unit. It fits inside the baggage compartment itself of my plane, a Beechcraft Debonair, otherwise known as a straight-tail Bonanza, or it fits also on the rear bench seat if I desired in the cabin. It does have a wireless remote control that's in line between the power source and the ice chest itself, so the whole unit can be powered on and off from anywhere in the cabin without having to have access to the toggle switches on top of the unit or the power cord itself. It is powered by a separate 12-volt deep cycle battery also mounted in the baggage compartment that's completely isolated from the aircraft electrical system. Here is an external view of the completed unit. You can see a bilge fan mounted through the top lid that draws air in through a heater core also in the top lid mounted underneath, through the unit, up and vented out to the pilot and co-pilot. That fan is mounted to the top of the lid with a piece of lightweight aluminum angle cut to size and bolted into place to the lid. There's also a couple of toggle switches. One toggle switch is for the bilge fan. The second toggle switch is for a bilge pump inside the unit. That's what's circulating the cold liquid through the heater core. And then a 12-volt cord which runs to a cigarette lighter adapter. Here is a close-up shot showing the two toggle switches and the cigarette lighter adapter power cord. Again, one toggle switch is for the bilge fan, the other toggle switch is for the bilge pump. All wiring is neatly concealed, protected,
and secured. Looking inside the unit that's completed, a bilge fan, which is underneath this little grill, draws air in through a small radiator underneath this louver cover here, mounted on the underside of the lid. And by the way, the reason for this steel grate is to protect the fan blades inside from any jostling ice during flight that might bounce up into that opening otherwise. Did put a bathroom exhaust fan cover on top of the heater core. That also protects against jostling ice. In this case, it's to protect the cooling fins of the heater core from being bent by ice that's jostled around during flight. Here you can see a picture of the unit being prepared for use. It's been filled with solid blocks of ice purchased from the local convenience store. Also, it's necessary to put 2 or 3 inches of water at the base of the cooler such that there's liquid in place to begin with so that the bilge pump can pump that cold liquid up to the radiator core and begin the cooling process. I chose to separate the unit's electrical power from the aircraft's electrical system due to the potentially high current draw and therefore overcapacity or exceeding the capacity of my airplane cigarette lighter plug adapter and associated circuit breaker. It's a marine battery box inside of which is a 12-volt deep cycle battery. On top of the box, as you can see here, is a wireless transceiver mounted directly in line with the battery and between the battery and the 12-volt receptacle externally mounted here. Between the wireless receiver and the 12-volt receptacle is an inline 20 amp fuse hidden inside the battery box. The wireless remote control allows the entire electrical power to be turned on or off from up front inside the cabin without having to have access to the cigarette lighter adapter cord for power or the toggle switches to the ice cold ice chest itself. A Y duct adapter was installed to simultaneously blow cold air on the pilot on this side and the co-pilot on the other side. For times when I'm flying alone in the airplane and therefore don't need to blow air onto the empty co-pilot seat, I installed a little vent closure here that snaps into place closed when I'm flying alone and simply pops open when a co-pilot is with me. This doubles the airflow to the pilot when flying alone. A performance test of the system was conducted to see what the ambient air temperature drop would be in operation. It was basically a winter day in Phoenix, which means it was 75 degrees inside the hangar, so it wasn't really a hot day, but the temperature drop should be similar for starting on a hot day. So before I turned on the system, ambient air was 75 degrees as shown here, Fahrenheit, and after just about 5 minutes of operating the system, it dropped to just under 42 degrees. So we had approximately a 34 degrees Fahrenheit temperature drop, which is in line with the best performance systems that I've researched online and seen other people test.
Okay, now let's turn to how to build the unit. Specifically, I'll describe the key materials and supplies needed down to the part number and supplier, and then give summary instructions along the way on how I constructed the unit. Okay, the first thing to be chosen, obviously, is the particular ice chest to be used as the basis for the cooling unit. In my case, I chose an Igloo Max Cold 70 quart cooler. And I bought it online. I can't remember what source, but it was $50 to $75 depending on where you purchased it from, and it was delivered to my home. I chose this for several reasons. First of all, it was as large a size as possible to fit within the space of my baggage compartment. This allowed a maximum amount of ice to be carried and therefore the unit to continue cooling for a long period of time during any flight. Secondly, it had a flat top. A flat top eased the installation of components that will eventually be mounted on top of the lid. Also, equally important, the underside of the lid was as flat as possible because components are mounted there as well. The next item to be purchased is what's called a heater core. It's essentially a small radiator. For the ice chest cooler, this piece is important because cold or warm air will be drawn in from the outside and into the ice chest through the cooling fins or across the cooling fins of this heater core. That's what cools the outside ambient air, and that air will be forced through the ducting to the pilot and co-pilot. The Spectre Premium 93003 heater core was used on, I believe, the year 2000-ish Ford Expeditions in their rear air conditioner system. It also, note at the top here, has tube-style outlets and inlets. This will ease the installation of the tubing for the eventual connection to the bilge pump. I did remove the foam strip around the edges here to avoid formation of mold or mildew due to the wet environment inside the ice chest. Next, we need to cut a hole in the lid of the ice chest that corresponds to the size, or actually slightly smaller than the size of the purchased heater core. I used a jigsaw to cut out a rectangular opening on the left side when looking at the unit from the front. Again, slightly smaller than the heater core size, so that I could avoid any gaps of air that weren't being forced through the fins themselves. Note that the placement of the cutout was such that on the underside I also had only the flat portion being cut out and allowed for the heater core to be mounted later without interfering with the non-flat portion of the lid. The next task was to mount the heater core to the underside of the lid, centered on the opening that had just been cut into that lid. To do this, and to make sure it was secure and held tight, I simply bent threaded rods into U-shapes. Then I drilled holes where those rods were to contact and penetrate the lid. When the rods were inserted and then nuts and washers were placed on top of the lid, simply screwed it into place. It held it very secure, pressed the heater core into place well, and minimized any air gaps that would have otherwise existed. These threaded rods can be purchased at any local hardware store. I used the number 1024 thread versions. They were just $2.48 each. I just needed two. Next, I purchased a marine bilge blower. This is a 12-volt fan made specifically for the boating environment because of the wet conditions. It has 4-inch diameter openings on each side and was purchased from Amazon.com for just under $36. This is the unit which will pull ambient air through the cooling fins of the heater core into the ice chest and then blow it out the ductwork onto the pilot and co-pilot. For reasons that will become apparent through the video, I also purchased an 8-foot long aluminum angle, 1/16 inch thick, from the local hardware store for $32. This is necessary to secure the bilge blower to the lid of the ice chest. I also used it later on to reinforce the floor of the baggage compartment to be sure it could handle the weight of the ice chest and marine battery. I used the jigsaw to cut a hole in the top lid of the ice chest corresponding to the diameter of the bilge fan, but not the diameter of the outer lip. This allowed the bilge fan unit to be placed down into the hole with the lip resting on the top of the lid. I then cut the aluminum angle to size and shaped it to allow securing through bolts and nuts through the lid, and then attachment of the bilge fan to the angle. This holds the bilge fan securely in place under all conditions. Another important item to buy is what's called a bilge pump.
A 12-volt unit, such as the one shown here, runs on 3 amps and pumps a lot of fluid per hour. In this case, 1,100 gallons per hour. In hindsight, that's probably way overkill in terms of the ice chest unit, but didn't make much difference in terms of the current draw. I purchased this unit off Amazon.com for $16. One challenge I encountered was how to attach the bilge pump to the tubing which runs up to the heater core. This was because of the outlet size of the bilge pump compared to the tubing size for the heater core. The eventual solution to this was to purchase a bilge and pump hose from Home Depot for under $10 and then simply cut out the portion indicated here. This will be important, as I'll show in the next slides. I eventually found the type of connector to make the connection possible. It was a 3/4 inch brass PEX-A barb by 3/4 inch Schedule 40 PVC straight adapter. Basically go to Home Depot and look up that part, and it's $9. It's a little bit hard to find, but it is the solution, as you'll see shortly. Flexible tubing is necessary in order to route the water from the bilge pump up into the heater core, and then eventually it's nice to have a tube which can be used to run water out of the heater core and onto the ground when you're trying to drain the entire ice chest without having to lift it and carry it out of the plane when it's full of water. Okay, at last, here was the solution all put together. We have the bilge pump. We have its diameter opening for the water to be pushed outward. We have the piece of the bilge pump hose over that outlet secured with stainless steel hose clamp. Then we have the special connector from Home Depot that takes us from what is usually PVC to barb. We secured that to the hose, the bilge hose, and the clear hose, again using stainless steel clamps. So now at last we have the water being drawn in from the ice chest unit floor, pushed through and into the tube, which goes up to the heater core. I routed the power lines from the bilge pump through the upper lid by drilling a hole close but not interfering with the area where the bilge fan was located. I also installed a strainer made of stainless steel over the bilge fan opening. This prevents jostling ice from impacting the fan blades during flight. I got the stainless steel strainer from Lowe's for $7.28. Note, it was a little bit hard to find, and it's the 4.7-inch version, so that it completely covered the 4-inch diameter hole of the bilge fan and allowed some space to be able to screw it into the lid and hold it in place. I also purchased 2 of bathroom exhaust fan vent covers, if you will, from Home Depot for $15 each. There are cheaper versions, but I purchased this particular model due to its increased strength and sturdiness for reasons that you'll see shortly. One of the exhaust fan covers was mounted on the underside of the heater core inside the ice chest unit, as shown here. It was secured in place by using picture hanging wire routed through small holes drilled into the exhaust fan cover and secured around the threaded rods. The purpose of this cover is to protect the heater core cooling fins from damage due to jostling ice during flight. Also note in this picture that the threaded rods hold the heater core in place on the underside of the lid very securely and very flush. In places where there was any gap, such as on the corners where air could otherwise get routed through there and not through the cooling fins and thereby lose efficiency, I simply used marine adhesive to fill in those gaps. The second exhaust fan cover
was mounted on the top side of the ice chest lid, centered over the heater core. In this case, the purpose was twofold. It did protect the upper surface of the heater core cooling fins from damage, and also gives the entire unit a very professional appearance. This exhaust fan cover is held in place by bolts, nuts, and washers through the cover and through the lid. Note that all of the materials used, bolts, nuts, washers, and so forth, were stainless steel to avoid the problem of corrosion over time. This is a picture showing the inside bottom of the ice chest unit. Here you can see the bilge pump connected to the clear tubing. The water, the 2 or 3 inches to begin with inside the unit for operation, is sucked in through the bilge pump, pumped up through the tubing into the inlet of the heater core, where it's circulated through the core, not shown in this picture, then is output through the exit of that heater core back down into the base of the unit. You'll also see a tubing here with a quick disconnect on the end. I'll explain this tubing in the next slide. Okay, so here you can see the tubing that we just showed connected to the outlet of the heater core. When the unit's simply in operation in flight, I disconnect this and leave the tube in the base or outside the plane somewhere at home. The water, therefore, the exit water, can simply drain back down into the cooler. When it's time, though, after landing to drain the entire ice chest unit of water, instead of having to lift the whole heavy unit full of water out of the plane and onto the ground and dump it, this quick disconnect tube allows the electrical system to be turned on, water pumped through the bilge pump, through the core, and then out into this exit tubing and onto the ground. So when all is said and done, the unit is light and can be lifted out of the plane, and the small amount of excess water dumped out easily. Next, let's turn to the electrical system design and installation. First, I purchased an inexpensive electrical outlet box from Home Depot. This is eventually where I'll show the various wiring was hidden from view inside the cavity. This gave a really professional, neat appearance, and to make sure that the colors all coordinated and it looked as professional as possible, I painted the original blue unit white. 2 toggle switches were necessary. One is an on-off switch for the bilge pump, and the other is an on-off switch for the bilge fan. These self-contained units were purchased off Amazon.com for a little over $7 each. Also necessary was the power cord itself. The power cord in my case was a 15 amp heavy duty model with a cigarette lighter adapter and ring terminals on the end. I purchased this off Amazon for $12. It has a built-in 20 amp fuse, heavy duty wiring to ensure that the system could handle any current draw that was being taken in for the cooler by the bilge pump and the bilge fan. Here is a picture showing the enclosure, the electrical outlet box, with the toggle switches mounted on top, and the wiring is all buried inside or underneath this electrical outlet box. Crimp connectors were used along with heat shrink tubing so that all connections were secure and waterproof, and all wiring was hidden from view. The only visible wiring exits through a grommet from a drilled hole in the side of the outlet box and secured to the angle with a little cable clamp. That is what runs up into the cigarette lighter adapter, which in turn plugs into the marine battery box. The entire system, as a result, concealed wiring and had a professional appearance to it. I purposefully installed a fairly long power cord. This was so that I could place the ice chest anywhere in the aircraft and be assured of reaching the power source. To store the excess power cord and make sure that the cigarette lighter adapter wasn't flopping around and hitting the ground, for instance, when I was on the ground in the hangar, I went down to the hardware store, picked up a couple of adhesive hooks, and installed them onto the back of the cooler.
The cord could therefore be wrapped around the hooks, keeping any excess neatly stowed, and when the aircraft ice chest cooler was outside the plane, it also kept the cigarette lighter adapter from hitting the ground and therefore being damaged. Next, let's turn our attention to the ducting system, which takes the air blown out by the bilge fan and directs it to the pilot and co-pilot. For this, I purchased a flex drain downspout extension from the local hardware store for under $9. I then used a cutoff tool to cut off this portion, throw it away, and cut off this portion and throw it away. The result is the right diameter of flexible tubing that can mount to the bilge fan and any other connections on the exit area. This ducting is advantageous since it is semi-rigid. It can flex and be shaped to the right size and placement in the cockpit, but then hold its position fairly well. Three other piece parts were needed to complete the ducting system. One was a three-way duct connector shaped in a Y, and it's used as a fan dryer vent hose, ordinarily 4-inch diameter, purchased from Amazon.com for $15. Also purchased a plastic dryer vent draft blocker, 4-inch diameter. This was the basis of what was going to be the vent for the co-pilot side that could be closed and open for when a co-pilot was or was not in the aircraft. I did trim off this flat flange using a cutoff tool and a Dremel because it was not needed, as you'll see shortly. Also needed were large stainless steel thumb screw clamps. This was necessary to secure a couple of pieces of the ducting subassembly together. They're easily available from Amazon.com for $9 each. In this case, I needed two. One of the large clamps was used to connect the ductwork to the Y adapter. The other clamp was used at the base, not shown in the picture, to secure the ducting to the bilge fan. Here you can see the valve assembly with the flange trimmed off, but yet still showing the interior flap. I secured this to the Y adapter with very small screws at the very edge of the Y adapter. This allowed the flap to still freely move and lock into place or be opened when needed. Placement of the attachment screws, shown here, was important to not interfere with the opening and closing of this little valve. Now I'll describe the external power source system. Again, I wanted to separate the ice chest air cooler from the aircraft's electrical system. So first, I purchased a marine battery box from Amazon.com for $40. This was a fairly deluxe unit that included 12-volt lighter adapters on each side, which you can't see here, a push-to-test switch, which showed you the state of charge of the battery, and recharge or power receptacles on either side, also connected to the battery, and with a tie-down strap. Since the cooler and the battery were both to be located in the baggage compartment of the aircraft, I would not have access to the toggle switches nor the power source while in flight. Therefore, it was important to enable wireless remote control, basically an on-off of the entire unit from the cockpit. Therefore, I purchased a wireless remote control transceiver online from Walmart for $13. The important aspect of this particular unit is it's capable of handling up to 20 amps. This ensured that the total amperage drawn by the bilge fan and the bilge pump would not exceed the capacity of the wireless control. Even though the marine battery box had two built-in 12-volt receptacles on the sides, the amperage they were designed for was on the edge, I thought, of the current draw that would be taken in from my cooler unit. Therefore, I purchased and installed on top of the battery box an external third outlet with specifically a higher amperage capacity, in this case 20 amps. Here I'm showing the assembled unit of the power system. So we have the battery box, the wireless, and the 12-volt receptacle. Not shown, but in line between the battery and these two units is a 20 amp fuse. To route and conceal wiring well, a hole was drilled in the back lid of the battery box, a grommet installed, and wiring to the wireless receiver was routed through here. Wiring associated with the 12-volt external receptacle was done via a hole drilled underneath here into the lid of the battery box. The end result, all wiring is concealed and protected and professional. This is an image of the battery box system with the lid lifted up a little bit so you can see the underside. Most of the wiring came with the unit. Just some of it was added due to the wireless receiver and third receptacle. You can see, for instance, the 20 amp inline fuse that was installed. The final consideration for the electrical power system was how to recharge the deep cycle battery when on the ground after a flight. After all, the ice chest air conditioner would drain that battery over time as current was drawn from the battery source through the ice chest air conditioner for the bilge pump and the bilge fan. So it turns out that most electrical battery rechargers have an SAE harness on the end, as shown here. I therefore purchased this adapter set off Amazon.com for $8. It has the SAE harness on one end, an inline 20 amp fuse, and ring terminals on the other. Now, as it turns out, the ring terminals were slightly smaller than the posts were for the battery inside the battery box. I already had a supply of the larger ring terminals, therefore I cut the originals off, crimped on, and used heat shrink to secure the right size terminals, installed this directly into the battery box onto the battery. Then you can see I routed the cord with the SE harness to the outside. So now, after flying, I simply plug in my electrical charger, run the existing line over to the SAE harness, plug it in, I'm good to go. The combined weight of the battery and the ice chest air conditioner is significant. It's critical that we limit the weight to that does not exceed the capacity of the aircraft it's being used in. Don't forget to account for G-loading, in other words, the increased effective weight of items during the flying of maneuvers inside the aircraft. To ensure that my baggage compartment flooring could withstand the weight and include any maneuver flying, I used the remainder of the aluminum angle to reinforce the flooring of my baggage compartment. I also added handles and tie downs to secure the battery and the ice chest unit. Here you can see the marine battery box subassembly installed into the baggage compartment and securely strapped down to the compartment flooring. I used a simple ratchet down strap from Harbor Freight for about $3 and a couple of simple handles from the hardware store secured down into the angle as the strap mechanism to hold the ice chest in place. Note that it held the entire chest down and held the lid closed, so the chest couldn't move and the lid couldn't open during flight. Here we see the unit loaded with block ice purchased from the local convenience store, also with a little bit of water added to the bottom to allow the bilge pump to begin operating immediately. It turns out that block ice works best, it lasts the longest, but any ice will be fine to use. And again, here's the completed unit, ready to be placed into the airplane and used. Here are a couple of photographs of the system installed into my aircraft. On the left is an image of the ice chest air conditioner placed into the baggage compartment of my particular airplane. Then on the right you can see the ducting that runs up over the back seat onto a couple of pillows and directs the air onto the pilot and co-pilot. And so, over the course of about 2 days of actual build time, we have a do-it-yourself ice chest air conditioner fitted custom into the rear compartment of my particular airplane with an isolated 12-volt battery source powering it for hours upon end. One final note: be sure that your curtains are closed or window coverings are on before getting out into the sunlight. After all, there's no need for unnecessary sunlight heating up the air inside the cabin and fighting the air conditioner. Thank you for watching the video. I hope you enjoyed it. I can't wait to get in the airplane and take off and test just how much cooler that aircraft interior is going to be in the long, hot summers of Phoenix. Happy flying to you all, and hopefully much more comfortable, cooler flying as a result.